When we go camping, we often use naphtha gas. It's a form of kerosene. It's often known as Coleman fluid. They all have about the same energy density of about 47 megajoules per kilogram, and it's 40 to 50 for most of the liquid fuels we use. The density of the fuel is 0.74 grams per cubic centimeter, so it's going to float really easily on water. I want you to calculate how much fuel you would need to bring your cup of coffee to a boil while camping when the stove is only 40% efficient, and it's probably worse than that. So let's say you're going to just raise the water temperature by about 70 degrees. For 1 milliliter of water and 1 gram are the same thing. So 250 milliliters is 2.250 kilograms. That times the heat capacity of water times the 70 degrees gives us 73 kilojoules. To get that 73 kilojoules of useful energy from the fuel, my rather interesting spelling, but this is already only 40%. So we needed 2.5 times more energy than this to get it. So we take 73 kilojoules divided by 0.4. We see that we needed 182.5 kilojoules of fuel, from which 40% of that energy is the 73 kilojoules we wanted. At 47.7 megajoules per kilogram, this means the mass of fuel we're going to need is the energy that we want divided by the energy the fuel itself provides per kilogram. And we get 3.8 times 10 to the minus kilograms. That's 3.8 milligrams. Sorry, 3.8 grams. So the density of the liquid can be solved for volume, mass over density, got a little trim off here, and we get 5.3 milliliters of camp fuel. So that's 2 or 3 squirts. I'd count on a lot more than that. I'd say probably 20 milliliters, so a couple thimblefuls full, but not much. But I used to do calculations like this to sort of roughly figure out how much fuel I'd need for a hike. But then in practice, you just start learning each hike how many bottles of fuel you'll need on your back to make your hike. Now, going down a cliff, when you rappel, you have to burn off all the energy of your height into friction on the rope. So the figure 8 was pictured in the assignment. So if you're coming down a 65-meter cliff, you have 52,000 joules of energy to get rid of, and you have to do it in 3 seconds. When you calculate this, you get 17 kilowatts, 17,000 watts. A hair dryer is 1,800 watts. This is the power equivalent of 10 hair dryers simultaneously aimed at the metal hitch in the rope. You're going to burn your hands and damage the ropes. Movies show fast rappels, and in practice, no. You got to go slow to avoid burns and destroying the rope. For people that are rappelling long distances, they often switch to this thing called a brake bar, which spreads the friction and damage on the rope over quite a bit and dilutes the heating so the rope isn't damaged as much. You turn on an 1,800 watt kettle. So the total amount of energy you need to bring the 2 liters of water to a boil, 663 kilojoules. 2 liters is like several coffee pots full up. It's more than any family needs in the morning. If the kettle is delivering the energy at 1,800 joules a second, and you need this much, it's like saying you need $663,000 and I'm paying you $1,800 an hour. How long is it going to take you to earn the money? So 663,000 joules at 1,800 a second, 368 seconds is how long it's going to take this coffee pot to come to a boil, 2 liters of water. 368 seconds, 10 minutes is 600 seconds. So this is 5 or 6 minutes. Okay, here's the detailed calculation. Now, the total energy you burned is going to be this wattage times the time. Okay? 368 seconds and 3,600 seconds in an hour. To do it by cost, We have 1.8 kilowatt hours. We can't use seconds. We use hours. We get 0.18 kilowatt hours. 0.18 kilowatt hours times 12 cents per kilowatt hour, bringing that 2 liters of water to a boil cost you 2 cents. Assuming 100% efficiency. A roller coaster of mass 1, 2, 3, 4, 5 kilograms is on a hill of 1, 2, 3 meters. It descends to a height of 0, then up a hill of 60 meters. What is the coaster speed at these two new locations? Well, the total energy is the same at all three locations. It doesn't matter whether it's here, here, here. It has no energy input. So the total energy at the start, where it's just sitting there at high altitude, would be this. That's our energy budget anywhere along its path. At the second point, it's descended to the bottom of the hill. There's no more height. There's only kinetic energy. Rearrange the formula, and we get 49 meters per second. At the third position, the energy is split. There's height on a lower hill and kinetic, and they must add up to the total energy available. So the potential energy on a 60-meter hill plus the kinetic energy equals this. Well, when the mass is on a 60-meter hill, this would be its total energy. So it multiplies out to 7 megajoules. So what we get is the 14.9 megajoules. 7 of it is now as height, and the rest of it is kinetic energy. And we get that velocity at the second position, or the last position. Now the elevator looks like a nightmare, doesn't it? But it's really quite straightforward. The first thing we have to do is get the total or net force on this situation. Let's assume downwards is positive. So the force 1 and force 2 are the forces on these two sides. Now force 1 is going to be the mass of the elevator plus the mass of the occupants. So it's going to be this times gravity. Where on this side, it's going to be 9,000 times gravity. This is pulling down, so I'll call it a positive direction. This thing here is pulling up on the elevator. I'll call it negative. So what we have is 8,750 down, 9,000 up, and I get 2,500 newtons up. Notice I kept the G out of the problem till the very end. It just saves my math a bit. You don't have to do that. With this 2,500 newtons up and a lift of 300 meters, we get 750,000 joules are necessary to lift the elevator. But the elevator is 80% efficient. So this is only 80% of what the elevator needed. The total energy the elevator used times 80% is this value. So to get total energy, we take the value we wanted, divide it by the efficiency, and we get 937.5 kilojoules. Set up the power formula, we get a 37.5 kilowatt motor. Now, does that seem high? No, we took into account subtraction due to the counterweight. Okay? The counterweight really made this life a lot easier for us. All right? And we're going up 300 meters. All right? All I have to do is, did I do this right? Is 875 plus 250 going to give us that 9,000? That would be the only source of error here. So these are the sort of test eligible questions, and I will put up a test review itemizing which one of these is most likely to be on the test.